Next is the time of emptying a tank through an orifice at its bottom. So you have a tank in the figure, you have an orifice at the bottom. Some liquid is filled up to a height of H1, that is indicated in the figure. Let an orifice be fitted at the bottom of the tank, required to find the time for the liquid surface to fall from height H1 to H2. So after some time, capital T, the liquid height comes down to H2 from H1. Initially the height was H1. After time T, the height is H2. Area of the tank is capital A. Area of the orifice is small a. Initial height H1, final height H2. Okay. At any time, the height of liquid from this orifice is small h. Okay. Consider a time before T where the height of liquid is small h. Okay. And the fall at that moment, that is time dt, is dh. Okay, so we had initially a height h1, then we had a height h2 after time capital T. So before time capital T, at an instant dt, we consider that the fall in height was dh. Okay, so the volume of liquid leaving the tank in time dt is A into dh. Okay, we consider that area into depth of fall gives you the volume. So area A into depth of liquid surface which is falling through the orifice, that is dh, will give you the volume. So theoretical velocity through the orifice V is equal to square root of 2gh. This we already know. Discharge through the orifice per second is dq, a small quantity, which is CD into area into theoretical velocity. This we already know. So dq is equal to CD into A into square root of 2gh. Discharge through the orifice in time interval dt is CD into A into square root of 2gh into dt. So this was per second. This is in time interval dt. Discharge through the orifice per second, we obtained that. Then discharge through the orifice in time dt, we also obtained that. Then the volume of liquid leaving the tank is equal to volume of liquid flowing through the orifice. So volume of liquid leaving the tank is A into dh. And volume of liquid leaving through the orifice, that we have calculated with the help of the equation. So we have both the quantities and we can equate both the quantities. Here the negative sign is given at the left side because of the decrease in head with increase of time. That is, as time proceeds, the height is decreasing. So that's why a negative sign is given on the left side. So minus A into dh is equal to CD into A into square root of 2gh into dt, or dt is equal to minus of A dh by square root by CD into A into square root of 2gh. Okay, here in this portion h is moved to the numerator. Okay, by integrating this equation we can obtain T. Okay, that is total discharge in time t. So integrating dt from 0 to t, and on left side, sorry, on right side we have the limits h1 to h2. Okay, so integrating right hand side we get minus a divided by cd into a into square root of 2g. These were constants. Integral of h1 h2 h raised to minus 1 by 2 into dh. So that finally comes to T is equal to minus A into CD into A into square root of 2g. These were constants, hence no change. So inside brackets after integration, h raised to minus 1 by 2 plus 1, the whole divided by minus 1 by 2 plus 1 H1 to H2. Okay. So minus 1 by 2 plus 1 comes to 1 by 2. Hence we have square root of H here. And in the denominator we have 1 by 2. So after taking 1 by 2 outside, we get minus 2a by CD into a into square root of 2g. Inside brackets we have square root of h2 minus square root of h1. Finally it comes to 2a into square root of h1 minus square root of h2, the whole divided by CD into a into square root of 2g. So for emptying the tank, that means the second height after time t becomes 0. That is, there is no liquid left in the tank. It is completely empty. So that condition is H2 is equal to 0. So time required for emptying the tank t is given by 2a into square root of h1, the whole divided by CD into a into square root of 2g. Now, time for emptying a hemispherical tank. So, in the figure, we have a hemispherical tank of radius r, okay, with the orifice at a bottom. Orifice is at bottom, radius r is there in the figure. Okay, an area of the orifice is A. The tank contains some liquid whose initial height is h1. Okay, and in time t, height is reduced to h2. So we have to find out the time t. Okay. So at any instant of time, the head of liquid over the orifice is small h, similar to the derivation what we have done just before. And x is the radius of the liquid surface at that point of time. Okay. So first the height was h1. So after some time, the height reduced to small h. So at that point of time, the radius of the surface has changed from, initially the radius was this much. Later it changed to x. Okay, that is the liquid surface is circular in shape in a hemispherical tank. So we are talking about x, that is the radius of the liquid surface. So x is the new radius of the liquid surface. Then area of the liquid surface is A is equal to pi into x square. And theoretical velocity is square root of 2gh. So, like the previous derivation, the liquid level is falling down. So the volume is A into dh, that is pi x square into dh. And the theoretical volume of liquid flowing through the orifice is given by CD into A into square root of 2gh. So, like in the previous derivation, we are equating equations 1 and 2. And we also have a negative sign here since the height of liquid is falling or decreasing with increase in time. So, pi x square into minus dh is equal to CD into A into square root of 2gh into dt. dt is there because this is the discharge per second. So, multiplying with dt gives us the total volume of the liquid. Okay. So, from figure, we know that in triangle OCD, we have OC is equal to R and DO is equal to R minus small h. So, CD is equal to X, which is equal to square root of OC square minus DO square. Okay, that is R square minus R minus H square. So, X square is equal to R square minus R minus H the whole square, which finally comes to 2RH minus H square. Okay, so substituting for X square in equation 3, we get minus pi into 2RH minus H square into dH is equal to CD into A into square root of 2gh into dt. So again we have to bring dt to the left side because the quantity we have to find out is dt, that is the time for emptying the tank, and all the other terms on the right hand side. So this finally reduces to minus pi by CD into A into square root of 2g into 2r h raised to 1 by 2 minus h raised to 3 by 2 into dh. So integrating like in the last derivation, if we integrate the left hand side we get capital T. So time for emptying we got it. On the right hand side we have the equation with limits h1 to h2. Okay, so we bring all the constants outside the integral sign and inside we have 2rh raised to 1 by 2 minus h raised to 3 by 2. Okay. So this becomes h raised to 1 by 2 plus 1 by 1 by 2 plus 1 and h raised to 3 by 2 plus 1. Sorry, here plus 1 is on the numerator. Okay, 3 by 2 plus 1. So this comes to 2 into 2 by 3 into r h raised to 3 by 2 minus 2 by 5 into h raised to 5 by 2. Okay, so finally this comes to the term after getting simplified pi into CD into A into square root of 2g, that is all the constants, and inside you have 4 by 3 into r into h1 raised to 3 by 2 minus h2 raised to 3 by 2 minus 2 by 5 into h1 raised to 5 by 2 minus h2 raised to 5 by 2. And in this equation, if we substitute h2 is equal to 0, we can find out the time required for emptying the tank. And that time is pi by CD into A into square root of 2g into 4 by 3 into r h1 raised to 3 by 2 minus 2 by 5 into h1 raised to 5 by 2. Now let's see a problem. A cylindrical tank is having a hemispherical base. The height of cylindrical portion is 5 meters and diameter is 4 meters. At the bottom of this tank, an orifice of diameter 200 mm is fitted. Find the time required to completely empty the tank. Take coefficient of discharge as 0.6. So in the figure, we can see the cylindrical tank with the hemispherical base, and there is an orifice at the bottom. So this is the cylindrical part, this is the hemispherical part. Height of the cylindrical portion is given as 5 meters, diameter of the tank is given as 4 meters. So area of cross section of the tank can be calculated. Diameter of the orifice is given as 200 mm, which is 0.2 meters, and area of the orifice is calculated. CD, coefficient of discharge for the orifice, is also given in the question. The tank is split in two portions. The first portion is hemispherical, second portion is cylindrical. So we have to calculate the time for emptying the hemispherical portion and time for emptying the cylindrical portion. And total time will be T1 plus T2. For portion 1, H1 is equal to 2, H2 is equal to 0. Then T1 is given by the equation for time for emptying a hemispherical tank. So here we know CD, we know A, which is the area of the orifice. Then we know H1 and we know H1 again. Okay, and G also is known to us. So we can find out T. Sorry, T1. Okay. Then for portion 2, H1 is equal to 2 plus 5, that is 7 meters. H2 is equal to 2. Okay, how H2 becomes 2 is that when H2 is 2, the cylindrical portion will be empty. So T2 can be calculated by the equation 2a into square root of H1 minus square root of H2 divided by CD into A into square root of TG. Here A is known to us, which is area of cross section of the cylindrical tank. H1 is known to us, H2 is known to us, small a is also known to us. So we can find out T2. So by adding T1 and T2, we get total time as 9 minutes and 29 seconds. Next is the time of emptying for a circular horizontal tank. So in the figure you can see a circular horizontal tank of length L and radius R containing liquid up to a height of h1. So liquid is only filled up to height h1. Let an orifice of area A is fitted at the bottom of the tank. So this is the orifice and area is given as small a. Time required to bring the liquid level from h1 to h2. It has to be derived. Okay. So consider at any time, that is dt, the height is h of the water surface and the height reduced by dh. Okay. So width of the liquid surface is AC at this particular time, that is here. Here, see the surface AC. DH is given here, H is given here. Okay, so at any time dt, H is the drop in level of liquid, that is height falls by dH. Okay. And width of the liquid surface is AC. Okay. Then surface area of liquid, the surface of the liquid in the tank will be rectangular. So L into AC, that is L into AC is the width. This is AC. So L into gives you surface area of the liquid. And AC from the figure, it is 2 into AB. If we consider the figure, AB is half of AC, B is here. Okay, so that is twice of square root of AO square minus OB square. If you consider the triangle AOB, AOB, and this is C. So AOB is a right angle triangle. So here AB square is equal to, or AB is equal to square root of AO square minus OB square. So this substitution, then it is equal to R square minus R minus H square, that is AO is R and OB is R minus H. Okay, that is, you can see here, this is R and this is H. And this distance is OB. Okay, so clearly OB is R minus H. Okay, so expanding this, we get finally AC is equal to 2 into square root of 2RH minus H square. Okay, so the surface area is L into AC, that is 2 into square root of 2RH minus H square. So volume of liquid leaving the tank in time dt is 2L into square root of 2RH minus H square into dH. That is area into dH. Okay. And volume of liquid flowing through the orifice, that is a theoretical equation, CD into area into velocity into dt. This is the theoretical discharge per second multiplied by dt gives you total volume of liquid flowing in time dt. So these two can be equated. Okay, so that is CD into A into square root of 2gh into dt, and volume of liquid leaving the tank can be equated. So we get this equation. Here negative sign is again introduced because with increase in T, H decreases. That is, as time proceeds, height of the water reduces because water is flowing out through the orifice in the bottom. So height is reduced. That's why always dh is given a negative sign. So we bring dt to the left side because dt is a quantity we have to find out. dt is equal to minus 2l square root of 2r minus h into dh divided by cd into a into square root of dg. So to obtain total time, we integrate. Integrating left hand side, dt becomes t, and right hand side has to be integrated from h1 to h2. So here all the constant terms are taken outside. Only 2r minus h remains inside. Okay, so it becomes 2r minus h raised to 1 by 2 plus 1 divided by 1 by 2 plus 1 into minus 1 for the negative sign of h from limits h1 to h2. So simplifying this, we get 4l divided by 3cd into a into square root of 2g into 2r minus h2 the whole raised to 3 by 2 minus 2r minus h1 the whole raised to 3 by 2. Okay, and we know that for emptying the tank, h2 must be 0. Okay, that is the height of the water must be 0. So here we substitute h2 as 0. We get 4l by 3cd a square root of 2g into 2r raised to 3 by 2 minus 2r minus h1 raised to 3 by 2. These are some problems for you to try out. Thank you.